Thank you very much. So hi everyone, I'm Geoffrey. And so this talk is going to be about homomorphic secret sharing optimizations and applications. It's a joint work with Elette Boyle, Niv Gilboa, Yuval Ishai, and Michele Oru. So a very common question in crypto is that of secure outsourcing. So you have a bunch of clients and they would like to perform some computation on their input with the help of a server. And here what we'll want is that we will want this to be done privately. We want the server to perform the computation for the client, but without learning anything about their private inputs. There is a natural solution for that in crypto, which uses fully homomorphic encryption. So put very simply, the clients encrypt their input, send that to the server. The servers can perform the entire computation without seeing anything and send back the result. Yet this has some issues. The first issue is with respect to privacy, which is that if the server colludes with one of the clients, then the privacy breaks down. A second issue is that of efficiency. So typically for computations where the clients would like the server to perform many computation on the input and return many outputs, then this means that there will be a large server-to-client communication, because what it sends back are large ciphertext. And there will be also some computation involved for the client to decrypt all those ciphertexts that will come back from the server. So from the viewpoint of the client, a better solution, and in fact an optimal solution, is to use MPC-based solution for secure outsourcing. So here, the client will just share their input between several servers, and the servers will perform some MPC protocol to evaluate the function privately on those shares, and they will end up with shares of the output that they send back to the clients. And so from the viewpoint of the client, that's optimal. Reconstructing is very efficient, very easy, everything is fine. Yet this again has some issues. The main issue is that it involves communication between the servers. And so this communication can incur some latency issues, but also it allows a traffic analysis where an attacker could look at the communication going on between the servers and find out an upper bound on the size of the function that the clients are willing to evaluate. And they might not want to leak that. And the last issue is that the servers have to know each other, which means that if one of the servers is corrupted, then the attacker will also know who is the other server, where he is, and so it might be more easy for him to corrupt it in this scenario. So we will look here at another scenario which aims at solving those issues. The communication pattern for the clients will remain the same. They have an input, they share it between the servers, and they will receive shares of the output from which they should be able to reconstruct very easily and efficiently their output. But we don't want the servers to be forced to communicate. We don't even want the servers to have to know each other or even to know that there is another server. What we want the server to do is just its job, get an input, do some computation locally, and send back the output. And that's it. So if it can be done, it's nice. And it's easy to see that it solves most issues that I mentioned before. The question is, can it be done? It can, with a cryptographic primitive that's called homomorphic secret sharing, that does exactly what you can imagine it does, which is exactly what I mentioned. You have an input, you can share it, and on those shares, you can locally evaluate a function so that you end up with shares of the output, f of x. Now, do we have homomorphic secret sharing schemes? For very simple functions, yes, just use Shamir secret sharing scheme, and you can evaluate any linear function. For all circuits, yes, also. We have, for example, a solution based on multi-key fully homomorphic encryption for all circuits. But this is more of theoretical interest because multi-key fully homomorphic encryption is even more expensive than standard fully homomorphic encryption. So what we looked at is an alternative solution which was developed by Boyle et al. In a beautiful Crypto 16 paper. So if you allow the correctness requirement to be relaxed a bit. So now we don't want any more perfect correctness, but we allow some small, non-negligible, but arbitrarily small failure probability. Then with this relaxation, it becomes actually feasible to build a homomorphic secret sharing scheme from the DDH assumption, so over groups where the discrete log is hard, for the class of low-depth circuits, which is already a class which captures quite a lot of interesting types of computation that you might want to perform. And in the same paper, they also showed that even this relaxed variant of homomorphic circuit sharing remains very powerful, even if the correctness error might be correlated with the input. So when an error happens, it might leak information about the input. If you use it carefully, you can still manage to do very non-trivial things, such as multi-party computation for low-depth circuits with optimal communication. So what did we do? We took this nice theoretical result that I will later to refer to as the group-based HSS scheme, and we showed that it is not just a nice theoretical result. We optimized it in several directions. We improved the computation overhead, we improved the size of the shares, we developed techniques to manage the leakage, and we looked at some scenarios in which this optimized group-based HSS scheme allows to give very good guarantees, like it leads to feasibility results that could not be achieved before with all other alternative techniques. And so to measure how efficient we can get, we also have an implementation and more. So I cannot talk about all of that in a few minutes, unfortunately. So in this talk, I will focus just first on an application. I will try to motivate a bit this construction, trying to convince you that it's cool and you want to use it, you want to have it, and you want to work on it. And once you'll all be convinced, I will describe some of the optimization we worked on. Okay, let's go. So here is our application. Might sound quite familiar to some people. You have two servers and you have a database. And in this database are regularly added some records. Think, for example, about newspapers. To each newspaper is associated an attribute vector. You can think of it as being a set of tags that describe what is in this newspaper. And there is Alice, our client, who would like to find out whether some new interesting records, say newspapers, have been added to this database. So this is known. This is called two-server private information retrieval. And there are existing solutions to solve this cryptographic problem. Yet those solutions typically consider the case of very simple queries where Alice will just want to retrieve a specific item from the database with its index. We want more. We would like to be able to let Alice be able to send very expressive queries. Ideally, what we would like to do is some things like, yeah, well, there is a set of tags, and I would like to retrieve all items from the database that contains most of these tags, or all of these tags. Or even more generally, Alice might want to retrieve privately from the database some items that are determined by a matching function, which can be, say, some arbitrary Boolean formula that takes as input her search query in the attribute vector. There is a trivial solution for that. Each time a new entry is added to the database, the two servers could simply send the entire attribute vector to Alice, and then she could do the job, look by herself whether something interesting was added to the database. Yet, if you think of Alice as being, say, a mobile phone that has subscribed to some RSS feed and that receives a continuous stream of information about those new entries that were added to several databases, this is clearly inefficient communication-wise. So what you would like to do is to see whether we can optimize the communication, if we can make it minimal. And we can. If we use homomorphic secret sharing scheme in a setup phase, Alice can share her search query, so the things she's interested into, between the two servers. Now, each time a new entry is added to the database, the servers will perform some computation on those shares that takes as input, so according to some matching function that can be quite complex, and that also take the attribute vector as input. And they will end up with a single bit, so that when Alice receives these bits, by XORing them, she can find out whether this new entry is interesting when it's 1 or non-interesting when it's 0. And if it's interesting, then she can use standard private information retrieval-based techniques to privately recover this interesting entry. And that clearly is optimal, because for each entry, she receives a single bit from each server. So we get something that can handle quite expressive matching function with a quite optimal communication. So we optimize that, we implemented it, and so, for example, if you want to evaluate some matching function that will be, say, a Boolean formula with 100 gates or with 100 threshold gates, then this can be evaluated in less than a tenth of a second. And this is on one core of a standard laptop, no fancy hardware here. So that's quite efficient. There is an issue of errors that I've not talked about yet, which is that in the homomorphic secret sharing scheme I'm talking about, the output can be erroneous with some non-negligible probability. But in fact, it turns out that in the scheme, the error is detectable, which means that the servers can, when they perform the computation, they can find out whether there is a high probability that an error will occur. And so in this case, the servers can, when this happens, simply send the entire attribute vector. And as errors happen only once in a blue moon, on average, that changes nearly nothing to the communication. On average, the communication is still very close to a single bit of communication from the servers to Alice. And there are other nice things that this can do. For example, you can imagine taking also into account input from a third party that will determine whether Alice should be authorized or not to get access to some of the entries. So you can handle some access control policies with quite complex policies. So I hope that this is a bit convincing, that it's a quite interesting primitive that can lead to new results. So let's look at how it's done. So in the group HSS scheme I'm going to talk about, what we can locally evaluate are RMS programs. This stands for restricted multiplication straight line programs. And the restricted multiplication will become quite clear. What is this kind of program? That's easy. You have two tapes, an input tape and a working tape. And you can do 4 types of things. First, you can download an input from the input tape to the working tape. You can add 2 entries of the working tape, and you get a new entry of the working tape. And that's the reason why it's called restricted multiplication. You can also do multiplication. You can multiply an entry of the working tape, but only with an entry of the input tape. And you get a new element in the working tape. And finally, you can output something. So if we could multiply 2 elements of the working tape, we would get something that's essentially a Boolean circuit. We can't. But this computational model remains quite powerful. It is sufficient, for example, to evaluate all of log space, all of NC1, branching program, or Boolean formulas, for those of you that for which this is something that you care about. So how is it done? Well, I won't have time to cover all of that, but a very nice unadvertised feature of our paper is that it contains a wonderful section about this, with a clean, well-written presentation that you should go and read if you want to find more about it. And so here I will just go directly to the important points. The important points is there is some group, and this group is just some discrete log hard group. There is no fancy structure that you have to assume about it. And there are some types of shares, and we will kind of manipulate those shares and switch between them. And the hard thing, the only thing that is really non-trivial, is that we need a protocol that does the following thing. We have multiplicative shares. We have 2 players with multiplicative shares of some g to the x. And they want to end up with additive shares of x. So there is a way to do that. That's computing a discrete log, which means that they cannot do that. Because in fact, there is no other way to do that. You have to compute a discrete log. So it's infeasible. End of the talk. So in fact, I'm a nice person. So I'm the kind of person usually willing to accept that people and algorithm can make mistakes. And here are the things to do. If you accept that this distributed discrete logarithm procedure can make mistake, magically it becomes feasible. Here is how. So I recall quickly what we want is we have multiplicative shares of g to the x. We want additive shares of x, the exponent. We view our group as a circle. In this circle, a point is a group element, and moving from one point to the next point is just multiplying by g. So I distinguish a random set of points over this circle using, for example, some PRF. And the conversion procedure I'm looking for, this distributed discrete log procedure, is just that. It takes as input a point, h, and look for the distance on the circle to the next distinguished point. Why does that work? Because if we both do that, the 2 players, and end up on the same distinguished point by doing so, the difference between our outputs will be the number of steps between our initial group elements. And this is exactly the discrete log that we're looking for, the value we're looking for. On the other hand, this procedure might fail if we do not end up on the same distinguished point when performing the procedure. And this happens when between our two starting points, there is a distinguished point, because then one of the players will end up on this distinguished point, and the other will end up in the next distinguished point. But the probability that this happens can be made smaller and smaller by reducing the number of distinguished points on this circle at the cost of making the running time higher and higher, because now it takes more time to find a distinguished point. And that's it. So at Eurocube 17, this procedure was heavily optimized. And in fact, this is what we want to optimize, because this is the core computationally hard step of the conversion procedure. And so the idea was the following. Instead of distinguishing point by evaluating a pseudo-random function, you distinguish them by looking at the most significant bits of the bit representation of your group element. And now, finding the first distinguished point in this conversion procedure is just finding d consecutive zeros for some parameter d that you have to tune to find out the error probability that you want and the efficiency. And it turns out that if you do that and use some specific groups, then this can be made extremely efficient. How? Just take a group G, which is a subgroup of Fp, where P is very close to a power of 2. And now take your generator G to be just 2. Now multiplying many times by G is just doing some bit shift and possibly some small addition with B. That's very efficient, and in fact so efficient that you can implement that with less than a machine word instruction per step of the conversion procedure. Yet, and that's where our optimization starts, it has some issue. One of them is that the event of one point being distinguished is highly correlated with the event of the next point being distinguished. Why? Because the point is distinguished by a bunch of consecutive zeros, and the next point is just the next bunch. So if the next bit is 0, the next point is distinguished. And intuitively, this makes the probability that two players detect the possibility of an error higher, and so overall, this lowers the efficiency of the algorithm for the same failure probability. So our first optimization, we separated the distinguished points. How do we do so? That was very, very hard. We look at the distinguished point, and if it is too close from another distinguished point, we say that it's non-distinguished. And that's it. Second optimization, way harder again. Instead of looking for a bunch of 0 in the stream, we look for a 1, then a bunch of 0 in the stream. Why does that help? Because recall that a failure happens when there is a distinguished point between our two starting points. And so if a distinguished point is determined by a longer pattern, then there are less distinguished points. So with this longer pattern by 1 bit, the number of distinguished points is twice lower. So the failure probability is twice lower. But on the other hand, the cost of performing the conversion procedure has not increased at all. Because when we were looking for the first occurrence of d consecutive zeros in the stream, once we find it, the bit that's right before that sequence is a 1, because that's the first occurrence of the string of 0. Hence, we've already found the other pattern we're looking for, which means when I pull that in the other direction, that for the same failure probability, simply by looking for this different pattern, saves a factor 2 in the amount of computation. Another thing we looked at is the fact that the event of an error is highly correlated to the maximum payload, the maximum distance between our starting points. And the previous work had to assume some bound on that and do some worst case analysis to get a bound on the error. So we developed algorithm to randomize the input of the players to ensure that they will be well distributed over the set of possible inputs. And by doing all of that, we can ensure that combined with a better average case analysis of the failure probability, we can save a factor 8 in the overall computational efficiency for the same failure probability, which overall saves us a factor 16 in computation to reach the same failure probability. And if we combine all of that with non-trivial machine level optimization, we also managed to improve the existing Eurocube 17 implementation and save again an additional factor 2 there. Then we overall save a factor 30 compared to the previous work for evaluating RMS multiplication, which is the core computational step in evaluating an RMS program. And you can find more about this implementation at this address. It's freely available. You can play with it if you want. Other optimizations we looked at how we could reduce the size of shares. So without going into all the details, a share, a level 1 share, because we have several types of share, is a bunch of Elgamal ciphertext. If you want to compress the size of a bunch of Elgamal ciphertext, there is a classical technique, which is called randomness reuse. But in our case, it does not work because randomness reuse requires using many keys, and the number of keys has an influence on the size of the shares in our HSS scheme. If we have many keys, we blow up the size of everything. So to recover the effect of randomness reuse, we developed a technique to work out randomness reuse with a single key and only public values. And this requires using a new assumption, but it's an assumption that holds in the chain group model. And by working out the details, we can get this factor 2 compression we were looking for in the size of the shares. Other optimization, and we've also worked on how to manage the leakage, because a failure can depend on an input. So when a failure happens, we can learn information about the input. We explain how to make this less likely to happen by using what we call leakage absorbing pads that can mask the input, so that when an input leak once, you learn nothing. When it leaks twice, then you learn something. This gives us a quadratic saving in the leakage rate. We also worked out some extensions to make it more efficient for branching program, threshold functions, and other types of interesting computational models. And we worked out further application. And one application I want to spend a minute on, if I have time to, is a case of generating correlated randomness. So that's a bit different. But if some of you like MPC, you might already know that many MPC protocols can be sped up quite well if the players have access to a source of correlated random coins. And it turns out that homomorphic secret sharing allows to generate quite efficiently correlated random coins. And by quite efficiently, I mean with very little communication. And so we put this as a new interesting research direction, which is still quite theoretical, but we have non-trivial advances, and there are many, many more things to do. So if you're interested into that, I encourage you to look and read the paper. There are many more work to do before this will become practical, but this is already cool, which is fine enough to do research on it. And that's it. So overall, we have many optimization, quite a number of applications. So I hope you found that interesting, and I will answer any question.
Maybe I don't know all the details in the preceding works, but I thought that you mentioned Elgamal shares. I thought that you need to go to BHHO to prove the security of the scheme. So are your modification also applicable to?
So yeah, so if you want to prove the security of everything under DDH, yes, you need to move up to this to BHHO. So here, as we were looking for practical efficiency, we were willing to we assumed the circular security of Elgamal. In addition, we also have some other assumption. I also described one additional assumption to compress the size. So yes, all of this does not assume only DDH anymore. It's more efficient, but with stronger assumptions on DDH groups.